I was told with this, I've got this, with this new format that I was only allowed to have one slide. So here's my slide, and we'll spend a lot of time exploring it. I'd like to thank the organizing committee for the opportunity to speak at this wonderful conference and to speak about my favorite topic, which is data. So what's the big deal with big data? Well, in transplantation in particular, we have a strong relationship with big data. Big data are available to us in unique ways in our field. This gives us power to do unique analyses, which we then need to apply to our patients. So what do I mean by that? Well, we transplant people who come into transplantation through a disease, end-stage kidney disease, end-stage liver disease, et cetera. So they don't come to us from home having never seen the medical system before. So for example, in the United States, Medicare tracks every single human being who is on dialysis because they pay for it. So we have the entire denominator of people seeking or potentially seeking transplant care. Then they join a waiting list, so obviously we have to get information about them through the waiting list so that we can allocate organs to them. So now we have the second denominator, which is all of the people who've ever been potential transplant candidates. Then they get organ offers, and we have to track those offers because they either accept or deny those offers, and it's very easy to keep records of all of that, so a lot of data there. We do the transplant, so we get information about the donors, about the recipients, and all of the information about the transplant-specific details. They take medications. For example, in the US, anytime anyone gets a medication prescription filled, that goes into a database. And so we can learn a lot about the diseases that they have through the medications that they take. So for example, we never tracked HIV status on our waiting list, but we recently did a project where we connected our waiting list to pharmacy claims data, and we were able to identify HIV-positive patients on the list because they're taking HIV medications. And then there's insurance claims. So anytime we do something to somebody, that gets billed to an insurance company, and we have the data from that as well. These data give us huge power. So we have very large sample sizes that we can study. The data are collected either in a mandated manner, like the waiting lists, the registries, or in an automated manner, like the pharmacy claims. When we do these studies, there's no selection bias. So we're not doing studies on homogeneous patients that agree to participate in a randomized trial at an academic center. We have data on every single person in the entire nation or the entire EU when we do a study like this. It's also a heterogeneous real-world population. So again, we're not just learning what happens to somebody when they go to a center that does 400 live donor liver transplants a year. We can understand what happens to people who go to smaller volume centers that wouldn't generally be writing up their results. And it's inexpensive. I have all the data on my computer. I can do analyses relatively quickly and relatively inexpensively. Well, we need these data, we need these inferences because, unlike other medical specialties, we deal with a scarce resource. So we have to create allocation policy. We have to create policies that will make people feel like they're being treated fairly, and that requires some mathematics. We want to make sure that transplant centers are providing adequate care, so we have benchmarking or report carding that we do with these data. We want to test new techniques, and again, if we test a new technique, we don't just want to do it at our center, but we want to do it at many centers. So for example, incompatible kidney transplants, only a handful will be done at a given center, but if we accumulate, if we study all of the transplants done across the nation, then we can make an inference not only about the outcomes of the incompatibles, but how they compare to compatible transplants, et cetera. And then insurance coverage. So every couple of years, one of the insurance companies decides that they're going to be creative and stop covering some procedure that we do in transplantation. And the ability to show that these are cost-effective and patient-effective in terms of life saved is very important as well. Well, there are techniques and challenges that come along with dealing with big data, and I'll just give you a sense of some of these. Obviously, we do a tremendous amount of regression modeling, and the big data give us all of the variables that can go into these regression models. But these are confounded by indication. What does that mean? That means that I might choose a given induction agent based on the patient's characteristics. So I need to account, when I'm comparing somebody who received drug A with drug B, I need to account for the fact that if drug A is used in low-risk patients and drug B is used in high-risk patients, then the patients who got drug B will do worse, and I need to deal with those things. We also deal with competing risks. So for example, if I'm on the waiting list and I use a regular regression model to study my access to getting organ offers, remember that I can also die on the waiting list, and I need to account for that statistically as well, and that can be quite complicated. I'm not trying to scare you, but I'm trying to make you aware that these things can be quite sophisticated statistically. There's also missing and messy data anytime we deal with large data sources, particularly ones that have not been accumulated specifically for our study. There is the whole field of risk prediction. So testing an association in a regression model is very different and requires much less robust statistics than creating a risk prediction model. And so when we create risk prediction, we need much larger sample sizes, cross-validation, et cetera. When we don't have data, we have to make up data, and in computer science we call that simulation. And so we have a whole field of simulation where we can take assumptions and create simulations based on that, and decision process modeling related to those. And I'll give you some of those examples from exactly within our field. I'll first give you a little example about what missing and messy data means. Here you see the donor height and the donor weight of deceased donors in the United States, and you discover something very interesting about our country. We have a very wide range of heights, ranging from donors less than 4 inches tall to donors who are 8'2". We have some donors that are 5'3" and 22 pounds. And actually, this may be quite realistic, but apparently we have some donors who weigh more than 400 kilograms. So there will be messy data when you take data from, for example, the US registry. So all of these data can be used to do things like effect modification studies, cost and policy analysis studies, simulation and optimization studies, risk prediction. I'm going to talk about 2 areas that I think are most important and have been in play recently. One is linkage and one is comparative effectiveness, and I'm going to give you some examples from that. So what is linkage? This is my cartoon, not the professional cartoonist's cartoon there. Linkage is taking data sources that we have from one source and finding some variable or combination of variables to link to another source. So for example, in the United States, we have the Social Security number. If we have somebody's Social Security number, we can link them to various other data sources that also have Social Security number. But another example might be, so if we have somebody's postal code, we know a lot about the community in which they live, and there are databases on community health measures. And we may be able to see, for example, Jesse Schold recently showed that where you live, not your own characteristics, but the health characteristics of those who live around you are just as strong of risk predictors for how you will do after a transplant as your own individual characteristics. And that was done through a linkage study. I'll tell you a little bit about a linkage study that we recently published looking at live kidney donors. So one of the questions we wanted to answer, I evaluate live kidney donors on a regular basis, and we wanted to be able to tell them what is your risk of dying from donating a kidney and what is your risk of getting ESRD if you donate a kidney, and in particular, your attributable risk, meaning what is that extra risk that you take as a donor that you wouldn't normally take if you didn't donate your kidney. Well, we needed large data sets to answer this question because these are very rare events, fortunately, after donation. And so to study rare events, you need to study huge numbers. We had the OPTN, the US Registry of Live Donors, but the US Registry keeps only the information about the donors, but not their long-term outcomes. And then we had general population studies called NHANES, the National Health and Nutrition Evaluation Survey. And that's, again, a cross-sectional study of tens of thousands of Americans, but again, with no long-term results. From NHANES, which represents the general population, we were actually able to create a healthy non-donor population, so people that could have been donors but didn't donate their kidneys and be able to follow them. And we followed them through linkage. So we used the Social Security number to link to two major data sources in the United States that have nothing to do with transplantation. One is the Social Security Death Master File. So in the US, when you get to a certain age, the government starts sending you checks. If you are dead, they will send a check and your neighbor will cash that check. So the government has very high incentive to know who is alive and who is dead. The government is like our Santa Claus or something. And so we were able to link the live donor data to the death master file and know who of the donors were alive and who were dead. And I'll tell you about a study we published in JAMA in 2010 looking at that. 4 years later, not because we're slow in analyzing data, but because these linkages take a huge amount of time and paperwork, we were also able to link to Medicare, Center for Medicare Services, CMS data. Medicare knows who's on dialysis. And so we were able to then identify which of these live donors and which of their healthy non-donor controls were on dialysis or developed end-stage kidney disease from donating. And we published that last year in JAMA. So in our first study, we looked at 80,000 living kidney donors. So again, this is the beauty of using big data is your N is very, very large in your studies. And we were able to show that compared to matched controls, when we study them for 12 years of follow-up, live donors don't have any higher risk of death compared to their healthy counterparts, which means that donating a kidney, whatever it does to you physiologically, does not cause you to die prematurely, at least for 12 years that we had data on. Then when we linked to CMS data, we were able to show that now from 100,000 live donors, because this database grows by 6,000 every year, the risk of developing end-stage kidney disease 15 years after donating is 31 per 10,000 if you're a donor, is only 4 per 10,000 if you're a matched non-donor. What does that mean? That means that there is attributable risk of kidney failure if you donate a kidney. I'm sure that you're all familiar with this study and the Norwegian study that did the same thing. And there have been studies from Canada, similarly by Amit Garg and his group, looking at big data and trying to answer these questions on kidney donors. So that's one example of linkage. What we're doing is we're taking all of the big data inferences that we're gathering from these linkage studies and building a calculator. So within the next year, you'll see a calculator like this online where you enter all the characteristics about the donor, and you can sit with them and say, your lifetime risk of ESRD if you don't donate is 0.4%, and if you do donate, it's 0.7%. I'll explain to you what those numbers mean, and you can decide whether you want to donate or not. So taking this not just in the research arena, but right back to patient care. Another area is comparative effectiveness. We do things to patients, and we want to know if those things that we're doing to them are worthwhile. Well, comparative effectiveness can be done in two manners. One, using observational data. So if we observed the people that we did thing A to, and we observed the people that we did thing B to, we can compare them using some statistical methods. The second way is what's called a Markov model or a stochastic decision process model, where we know some of the things, but we can't observe the counterfactual because we didn't do the counterfactual to enough people, and so we draw on data from all sorts of sources, and I'll tell you what I mean by that in a little bit. So observational data, basically we can answer questions like, if you're on the waiting list and there is an organ being offered to you, what is your survival advantage of accepting that organ or waiting on the list for the next best available organ? We did this recently looking at high KDPI kidneys. And so basically we have an observational study that happens naturally. This is sort of a natural experiment because some people will decline these organs, some people will accept these organs. And we can observe those who've accepted them and observe those who decline them and see how they do. Here's an example from a study that we did a few years ago on incompatible kidney transplants. So what was happening is the insurance companies were trying to tell us that we should not do incompatible transplants because they're too expensive, because we have to pay for plasmapheresis, and they didn't want to pay for this. And so we had to prove to them that the desensitization procedure that we were putting patients through actually provided a survival benefit. And so what we did was we looked at all the patients that we desensitized at Johns Hopkins, and we found people using big data, using the waitlist database. We found people who looked just like them on the day we transplanted them, but didn't get an incompatible kidney transplant and instead remained on the waiting list, and whatever happened to them happened. Either they got transplanted, they didn't get transplanted, et cetera. And we were able to show the insurance companies that by paying for a little bit of plasmapheresis, they were actually doubling the life expectancy of these patients. They're giving them twofold survival benefit from undergoing this treatment. Now, Markov models are a little bit more complicated. In these cases, we cannot observe the entire treatment group and the entire comparison group, and we have to draw from other data sources and create a simple little thing like this. This is an example of a Markov model to help patients understand whether they should accept organs from donors in the US that we call CDC infectious risk donors. These are injection drug users, et cetera, that have a risk of carrying undetected HIV or hepatitis C. Now, this is a relatively recent category of donors, and one that we don't have a lot of observational information about directly from transplantation, but we do have a lot of information from other cohort studies outside of transplantation. And what we can do is build this decision process model where we have a patient and they have to make the decision, do I accept this kidney or not? Now, this kidney has some probability of carrying an undetected infection, and we mathematically model that probability. If they get that infection, they have some probability of dying from that infection, and we can model that based on what we know about survival with that infection, et cetera. And patients cycle through these Markov states where if you get the transplant, now you're in the post-transplant state. If then that transplant fails, you move back to the waitlist state, et cetera. And we can use a lot of big data to inform these things. At the end of the day, what happens is the patient gets a calculator again, and this is available online already, came with our AJT publication on this model, and we can enter all the information about the patient and the donor and say to them, if you accept this organ, this is your estimated survival curve. If you decline this organ, this is your estimated survival curve. So another way of doing that. What's the big future for big data? Well, there are more and more countries forming registries, and our registries are getting larger just because we're doing more transplants, and are getting richer because it's easier to collect new data. As you heard from the last speaker, these electronic health record systems are becoming more robust, giving us more data feeds, and becoming more homogeneous, more universal, where we can take all of those data and put them into a single system. There are efforts being made by the NIH and other funding agencies to have investigators put their data online, so to make more raw research data available to other people so that we can then combine data from studies at the patient level rather than at the meta-analysis level, which is not as ideal. There's a ton of work being done in biologics, and I haven't even touched on that because that's been discussed in several other talks at this conference, and we hear a lot about how we get big data on genetics and epigenetics and molecular markers and biomarkers and things like that. For those who are in your training or earlier in your career and are interested in creating a career in big data, just a couple of pieces of advice. The first is to decide what your role will be in dealing with big data. Are you going to be a soloist, which means are you going to be the one who creates the regression models and designs the statistical analysis, et cetera? Or are you going to be a collaborator where you bring from the trenches where you work the interesting clinical questions, you learn enough about statistics to describe them to a team of statisticians who can do the technical work, and then you know how to bring that back to your patients. And in order to achieve your goal, you need to think about that role, and for that role, you need training. So if you're going to be a soloist, you should probably get formal training like a PhD in biostatistics or epidemiology. If you're going to be a collaborator, you might just either learn by osmosis from another group that happens to be at your center, or get a high-level sort of introductory course in the kind of things that I'm talking about so that you can interface with other groups. You need resources for this, obviously, including collaborations, and you need mentorship and I always recommend for people to find mentorship both within their institutions and outside their institutions, because you can bring something new to your own institution. I would like to acknowledge my own research group at Johns Hopkins, which I direct, which is comprised of a number of epidemiologists, physicians, surgeons, computer scientists, research associates, people who gather the data for us and help analyze the data. And again, I thank you for your time.